Hello, good evening everyone, and welcome once again to my channel. And welcome to lecture number 6 of Maths Optional. This is lecture number 6 only, I guess. Okay, correct me if I am wrong. So, welcome to lecture number 6 of Maths Optional. And in this lecture number 6, let's start with the fifth property. Uh, the video went off abruptly at that point. So we will continue with the fifth property. If the sum of square of fifth property of orthogonal matrices, if the sum of square of each row is unity and the sum of product of any two rows is equal to 0, then the matrix is always orthogonal. Okay, so let me explain you the meaning of this. Suppose I have a matrix of this kind. Okay, A, B, C, D, E, F, G, H, I. Suppose I have a matrix of this kind, 3 cross 3 matrix. Okay, so sum of the square of each row. So this matrix will be orthogonal. This matrix will be orthogonal if and only if, okay, the sum of square of the elements of each row. Okay, sum of square of elements of each row is equal to unity. Okay, so these conditions must be satisfied. G square plus H square plus I square is equal to 1. Okay, okay, so sum of square of each row is unity, and the sum of product of any two rows. Okay, pick up any two rows. Suppose I pick up these two rows, so AD plus BE plus CF is equal to 0. Okay, see, similarly if I pick up these two rows, last two rows, then DG plus EH plus FI is equal to 0. And similarly if I take these two, then it will be AG plus BH plus CI is equal to 0. Okay, so this a matrix which satisfies these conditions which I have explained over here, so such a matrix will be called as an orthogonal matrix. So let us solve an example based on this. Okay, which might be asked in your exam. So something of this kind might be asked in your exam. Okay, so determine the values, of alpha, beta, gamma when the matrix is given over here: 0, alpha, alpha. Let me erase this. Okay, 0 alpha alpha, 2 beta beta minus beta, gamma minus gamma gamma. Determine the values of alpha, beta and gamma when this matrix, this particular matrix is orthogonal. Okay. Now we know that alpha, beta, gamma, how many unknowns are there? The approach should be such that these three are your unknowns. What are these? These three are your unknowns. So the number of equations which I need, there are three unknowns. There are three unknowns. So the number of equations which I will need is 3 in number. Okay, number of equations which I will need is also 3 because there are 3 unknowns. So I will need 3 equations. So I will start solving it and I will write that I will apply these conditions over here. Okay, and I will make some equations. So as soon as I make the equations, so I get some equations of this kind, that 0 square plus 4 beta square plus gamma square is equal to 1. That implies you have to do it yourself. Okay, you will understand it yourself. This is the most easiest part. Okay, so this is equation number 1. Similarly, if I take the second row, then this will be the equation. Okay, so this is your equation number 2, and the third equation, take any two rows, multiply the, okay, multiply the elements is equal to 0. So your third equation becomes 2 beta square minus gamma square is equal to 0. Okay, this is your equation number 3. This is gamma, by the way. Okay, this is gamma square. Okay, now how to solve these equations? This is a nursery thing. Okay, you will add these 1 and 3 equations, so you can clearly see that this gamma square and this gamma square cancels out. Okay, so as that gamma square cancels out, so I get 6 beta square is equal to 1. That means beta equal to plus minus 1 by root 6. Okay, and similarly I can find out the other values too. Okay, when I put this beta here, then I get gamma, then with the help of beta and gamma I find the value of alpha from here. I don't think there is any need to show that how to solve the equations. It is a nursery thing which everyone must know. Okay, very small classes you have learnt all these things. Okay, so let's move on towards the next question. Similar, on the similar lines, one more question might be asked to you. Question 2. Determine whether A is orthogonal or not. And your matrix A is given over here. It is of this kind: 1 by 3, 2 by 3, 2 by 3, 2 by 3, 1 by 3, minus 2 by 3, minus 2 by 3, 2 by 3, minus 1 by 3. Okay, we have to determine whether this is orthogonal or not. So it is very clear that you will square this, square this, square this and add them. Okay, it should be equal to 1. Then square this, square this, square this and add them. That should also be equal to 1. Square this, square this, square this and add them. This should also be equal to 1. Okay. Then product of these two plus product of these two plus product of these two, that should come out to be 0. Okay, then product of these two plus product of these two plus product of these two, that should come out to be 0. Okay, then product of these two, product of these two plus product of these two. Okay, means product of these two plus product of these two plus product of these two, that should also be come out to be equal to 0. Okay, so it is a very obvious that it is very easy to show this is orthogonal. Okay, so I don't think there is any need to show it to you by solving. Okay, it is very easy thing. Okay, now let us do one more example of that kind. Now a little bit different example. Okay, determine determine whether A is orthogonal or not. Okay, so your A is given like this: cos theta 0 minus sin theta 0 1 0 sin theta 0 cos theta. So how will you do it? Similarly, take the first square this plus square this plus square this, that should be equal to 1. So your first equation becomes this thing. Okay, this should come out to be equal to 1. So is it coming out to be equal to 1 or not? You know that sine square theta plus cos square theta is equal to 1. So this is satisfied. Then this is square plus this is square plus this is square means 0 square plus 1 square plus 0 square. That is also coming out to be 1. Means the second row also satisfied the condition. Then this is square plus this is square plus this is square. So what will it look like? Minus sine theta square means minus sine theta whole square plus 0 square plus cos theta square. Okay, so this is clearly minus sine theta will turn out to be sine square theta plus 0 should be ignored, so cos square theta. So that is clearly 1. So third row also satisfied the condition. Then product of these two means 0, product of these two means 0, plus product of these two means 0. So 0 plus 0 plus 0 means what is that? 0 plus 0 plus 0 means the product of these two rows added together has given you 0. Then we will look at these two rows. So this row multiplied by this row minus cos theta sin theta. Okay, this multiplied by this is 0 plus sin theta cos theta. So the product of these two cancels out product of these two. So again it is giving you 0. Okay. So these two satisfied the condition. Okay, and the means the first and second row multiplied together satisfied the condition. First and third row multiplied together satisfied the condition. Okay. Now second and third row come. So second and third row similarly 0 0 0 0 plus 0 plus 0 will come. Okay, so all the conditions are satisfied. So clearly this matrix is orthogonal. Okay. So in this way you can prove the things. Now we will move on towards our next question, okay, which is question number 4. So let's move on towards our question number 4, okay. Yes. So the question number 4 says it is something of this kind. Question 4. If LR, comma MR, comma NR, where R equal to 1, 2, 3, B, D, direction, cosines of the three mutually perpendicular lines referred to an orthogonal Cartesian coordinate system, then prove that, okay, then prove that L1, M1, N1, L2, M2, N2, L3, M3, N3, okay, is an orthogonal matrix. So clearly, uh, R equal to 1 to 3, what does this mean? So you will put R equal to 1 to 3 here. So you can see that L1 comma M1 comma N1, L2 comma M2 comma N2, L3 comma M3 comma N3 will be your direction cosines, okay. So three mutually perpendicular lines have L1 M1 N1, L2 M2 N2, L3 M3 N3, like that, the direction cosines of three mutually perpendicular lines. So this is orthogonal Cartesian coordinate system, okay. You know this very well that orthogonal means 90 degree. So even if this word orthogonal wasn't written there, even still the meaning would have been the Cartesian coordinate system, okay. So orthogonal Cartesian coordinate system just means that the xyz axis of the Cartesian coordinate system are perpendicular to each other, okay. Xyz axis are perpendicular to each other, that's what is meant by this, the word orthogonal, okay. So we have to prove that these three mutually perpendicular lines which have L1 M1 N1 L2 M2 N2 and L3 M3 N3 as their direction cosines, then the matrix formed by them, like this, the matrix of this kind which is formed by their direction cosines is an orthogonal matrix. We have to prove this. So let's start. So first of all, solution I will write. Let A is equal to what? Your L1 M1 N1 L2 M2 N2 L3 M3 N3, okay. This is what is your first matrix, okay, which is given to you, which is you have to prove. So you have considered it to be equal to capital A. So clearly A transpose, how A transpose will look like, I had told you in the previous classes that for transpose to be found out, this first row will become the first column, okay, this second row will become the second column, this third row will become the third column, okay. So let's write over here L1 M1 N1, okay, L2 M2 N2, and over here L3 M3 N3, okay. This is what is the transpose of this, okay. Now we will take the product. What we will take? We will basically take the product of this A and A transpose, because you know the by definition of orthogonal matrix, product of a matrix and its transpose should come out to be identity, right? Let me write over here. By definition of orthogonal matrices, if A is an orthogonal matrix, then it should satisfy the condition. Which condition? The condition of this kind, A transpose is equal to I is equal to A transpose A. This condition it must satisfy. So if we are able to prove that A satisfies this condition, then we can prove that A is orthogonal, okay. So we have to simply show that A satisfies this condition. So now you have written A and A transpose like this. So we will take the product of A and A transpose now. So let's take the product of A and A transpose. A transpose is equal to, what does it look like? L1 M1 N1, L2 M2 N2, L3 M3 N3, okay. And once again we will take the transpose and multiply it, so it will look something like this: L1 L2 L3, okay. Then we have M1 M2 M3, then we have N1 N2 N3, okay. And as soon as you take the product, so what will happen? How to take the product? You know this very well, right? You know how to take the product. Now let me show you how to take the product. Okay, first of all, this multiplied by this will happen, okay. This row, the row of first will be multiplied by the column of first, okay. Then the row of second will be multiplied by the column of second, then the row of third will be multiplied by the column of third, and you will keep on writing the corresponding terms, okay. So this will be multiplied by this and this, okay. Just a second. This will be multiplied by this and this, then this will be multiplied by this, this and this. Then this last row will be multiplied by column number 1, column number 2, column number 3. So like that. So let's write over here. What do we get? What do we get? So L1 multiplied by L1 first of all, because this multiplied by this is going on now. So term by term. So L1 square plus what will happen? M1 square plus what will happen? Plus N1 square. Okay. So this has come. Now the second term. Second term is this multiplied by this one. Okay. This one. So let's multiply that also. So you will get L1 L2 plus M1 M2 plus N1 N2, right? Then the third thing, then this column, this row multiplied by the last column. So term by term you will get what? L1 L3 plus M1 M3 plus what? Plus what? N1 N3. Okay. So similarly you will get the terms. Now I will write fast. L1 L2 plus M1 M2 plus N1 N2 over here. Over here you will get L2 square plus M2 square plus N2 square. You over here you will get L2 L3 plus M2 M3 plus N2 N3. And the last row, let me write on the next page, the last row of that matrix. Okay, the last row which you will get will look something like this: L1 L3 plus M1 M3 plus N1 N3. Okay, then you have L2 L3 plus M2 M3 plus N2 N3. Then you have L3 square over here. Over here what you will have? What will you have? Over here you will have like this. Okay, right? So what are all these things? All these things are basically your in continuation you have to write. Okay, these two rows and then this third row you have to write in continuation. Because of lack of space I have written it on next page, but you have to write in continuation in the matrix form like this. Okay, or like this. Okay, now we know this very well, that the matrix we have written over there we have got some you know this very well, but you will learn later on. You might not be knowing this right now, that the direction cosines of mutually perpendicular lines. Okay, direction cosines of three mutually perpendicular lines. You will learn this later on in the upcoming classes, but for the time being just accept the facts as it is. Or you must have learnt in your graduation or post graduation the direction cosines of three mutually perpendicular lines uh, with direction cosines L1 M1 N1 L2 M2 N2 L3 M3 N3. So direction cosine of three mutually perpendicular lines satisfy, okay, the relation. Which relation? They will satisfy this relation L1 square plus M2 square plus N1 square. Okay, L1 square means, for example, you take the direction cosines like this. Okay, L1 M1 and N1 N1 N1, L2 M2 N2, L3 M3 N3. Okay, so what will be the relations? So you know this very well, that the direction cosines when squared and summed together, the direction cosines when squared and when the squares there, the sum of their squares is taken. Okay, when this L1 M1 N1 will be squared and its sum will be taken, it is going to be 1 by the property of direction cosines. You know this very well. Similarly for this the same will happen. Okay, so you will write L2 square plus M2 square plus N2 square is equal to 1. Similarly you can write L3 square plus M3 square. Okay, you can write L3 square plus M3 square. This is by the property of direction cosines, that for a line having direction cosines L1 M1 N1, the the sum of the squares of its direction cosines always comes out to be equal to 1. You must have learned this in your graduation. Okay, now we will apply the orthogonality condition. Three mutually perpendicular axes were there. Three mutually perpendicular lines were given to us. Okay, so these three equations, okay, these three equations were from the property of direction cosines. So these three equations, L1 square plus M2 square plus L1 square plus M1 square plus N1 square plus L2 square plus M2 square plus N2 square plus L3 square plus M3 square plus N3 square, all these three equations, these are from the property of direction cosines. Now we will use the perpendicular lines condition for perpendicular lines. Okay, perpendicular lines condition on direction cosines. So what is the perpendicular lines condition on direction cosines? Suppose L1 M1 N1 is your line number 1. Okay, line number 1. L2 M2 N2 is your line number 2. L3 M3 N3 is your line number 3, and it is given that 1 is perpendicular to 3, 2 is perpendicular to 3, and 1 is perpendicular to 2, like this. Okay, then the direction cosines satisfy the following relation. Which relation? Okay, which relation? This multiplied by this, okay, plus this multiplied by this, plus this multiplied by this is equal to 0. Okay, is equal to 0. And then this multiplied by this plus this multiplied by this plus this multiplied by this is equal to 0. Then this multiplied by this plus this multiplied by this plus this multiplied by this is also 0. Okay, so let me write these equations over here. Okay, so what do you get? L1 M1 plus L2 M2 plus L3 M3 is equal to 0, you get. Then what you get? Okay, how did you get this? By this property. Okay, L1 let me Okay, sorry. So from here you will write the equations like this. Okay, this is a different condition. This is different condition. Leave this for right now. Okay, for the time being, leave that. But look at this. Look at this condition. L1 L2 L1 L2 plus M1 M2 plus N1 N2 plus N1 N2 plus N1 N2. This is equal to your 0. Then you have L1 L3 plus M1 M3 plus N1 N3 is equal to 0. Then you have L2 L3 plus M2 M3 plus N2 N3 is equal to 0. So these are the properties. Now there is one more property. Which property? This property is satisfied by these lines, these properties. Okay. Now there are some more properties which are satisfied by these lines, mutually perpendicular lines. Okay. The properties are something of this kind that when I take the product of these two, okay, let me show you these two, okay, product of these two and product of these two, okay, this is also by the condition of orthogonality, means perpendicularness of two lines, okay, perpendicularity of two lines. So when I add these red ones, okay, when I add these red ones, I get 0. Similarly, when I add this one with this one with this one, I again get 0. Okay. And similarly, in the last, when I try to add this and this, okay, product of this with this, okay, and product of this with this and product of this with this, okay. So when I add these, I again get 0. So my other equations will be something like this. They will look something like this. What, how they will look? They will look something like this. L1 M1 plus L2 M2. This is also by the orthogonality condition of lines. Okay. This is also by the orthogonal lines property. So M1 N1 plus M2 N2 plus M3 N3 is equal to 0, and you have N1 L1 plus N2 L2 plus N3 L3 is equal to again your 0. Okay. So by putting all these things, okay, these three equations, these white equations, these green equations, and these equations, which one? These equations 1, 2 and 3. Okay. So by putting these equations in this matrix which you had got, A transpose value which you had got over here, this big one, big matrix which took 2 page, okay, which took 2 page, if you clearly substitute these values in that matrix, so you get the value of A transpose equal to, when you substitute all these values based on the orthogonality of lines condition, you clearly get these values, okay, 0 1 0 and 0 0 1, okay, and means that is, this is identity matrix, okay. So you got this. Similarly, in a similar fashion, similarly in the examination you have to prove this also, by the way. Similarly, A transpose A is equal to I can be shown, can be shown. So clearly A transpose comes out to be equal to A transpose A, that comes out to be equal to your I. So by the definition of orthogonal matrix, that implies that A is orthogonal matrix. right? Now write one note over here, okay? Write one note which I had forgotten to tell you previously, okay? Note. Although this is not related to all this stuff, it is not related to all these stuffs. This is something different kind of note which you must remember, and which is quite common sense type of note, okay? Common sense type of note, that null matrix null matrix is always null matrix is always symmetric and skew symmetric both. Null matrix is always symmetric and skew symmetric both. Now the example is over here. For example, this null matrix, okay? Let me write a lot of zeros. This null matrix. So clearly, this is both symmetric and skew symmetric. You can apply the conditions of symmetricity and skew symmetricity and check this, whether this is skew symmetric or not, or whether this is symmetric or not. You will find that they satisfy all the condition of symmetric also and skew symmetric also. So they are both. Null matrices are both. Okay. So you have to remember this thing. Now we will move on towards our next thing. Okay. So let's move on towards our note number 1 of this class. Yes. So so let's move on. The property number 1. Okay. Every square matrix can be uniquely written as a sum of symmetric and skew symmetric matrices. So every square matrix can be uniquely written as a sum of symmetric and skew symmetric matrices. So let's suppose that A is any square matrix. Okay. So the proof of this will be in two parts. Okay. The proof of this statement will be in two parts. Which two parts? Existence and uniqueness. Okay, existence and uniqueness. In this way, the proof of this statement will be done in two parts: existence and uniqueness. Okay, so existence will prove, okay, existence will prove that every square matrix can be represented as sum of, okay, so existence will prove that such a representation exists, whereas uniqueness will prove that if there is any such representation, then that representation is one and only one. Only one representation is there. Okay. If there is any other representation, then it will be equal to the first one. Okay, so this is the thing. Now we will actually start the proof. So proof existence. Okay, let A be any square matrix. So existence we will prove like this. Let A be any square matrix. So I can write A to be equal to like this. Okay, half A plus A transpose plus half of A minus A transpose. Now what does this mean? Okay, okay. So this is very obvious fact, because this half A, this half A and this half A will become complete A, and half A transpose and minus half A transpose will cancel out. Okay, so this is quite obvious representation. So I let this to be equal to P plus Q. I let this to be equal to P plus Q, where it is obvious that what is P? P is your, okay, where P is your half A plus A transpose. Okay, and Q is your half A minus A transpose. Okay, so if we are able to prove, okay, if we are able to prove that this P, okay, if in case we are able to prove that this P and this Q are symmetric and skew symmetric matrices respectively, if we are able to prove that P is symmetric and Q is skew symmetric, if we are able to prove that, then we can prove that every square matrix A can be represented as P and P plus Q, where P is symmetric and Q is skew symmetric. Okay, so in order to prove P to be symmetric, in order to prove P to be symmetric, P to be symmetric and Q to be skew symmetric, we will do the following steps. What we will do? We will apply the definition of symmetric matrix. What do we do for symmetric matrix? For symmetric matrix, we find out the transpose. If the transpose is same as the original matrix, then it will be symmetric. In order to prove Q to be skew symmetric, what we will do? We will take Q transpose, and if Q transpose comes out to be equal to minus Q, then that will be a skew symmetric matrix. Okay. So in order to prove that, we are doing this. Now P transpose. So what will it look like? It will look something like this. Okay, this is bracket half A plus A transpose transpose. Okay, then what will happen? This half will be as it is, and A plus A transpose will be there, and whole transpose will be there, right? Then what will happen? This will be by distributivity property. This will simply distribute over it. Okay. Then what will happen? A transpose transpose, you know very well that this will be A transpose will remain as it is. A transpose transpose, what will happen to A transpose transpose? Transpose of transpose is the original matrix, so it will be the original matrix. So clearly this is what is your P transpose. Now if you rearrange the terms, what is it looking like? A plus A transpose. You simply rearrange the terms. Okay, let me write properly over here. Okay, so you rearrange the terms, and what does it look like? A plus A transpose. You simply wrote this over here and this over here. Okay, so nothing else, and addition is commutative, so you wrote it like that. Okay, so this is equal to your what? P. So P transpose has come out to be equal to P. So when the transpose of a matrix is equal to the original matrix, it is a symmetric matrix. So that implies that P is symmetric. P is symmetric matrix. Similarly, we will take Q transpose. Now what is your Q? Q is your half A minus A transpose. So you will take the transpose of Q. So Q transpose will look something of this kind. Half A minus A transpose whole transpose. Okay, it will look something like this. Then what will happen? This half will come out, and it will be A minus A transpose whole transpose. Okay, then it will be half A transpose minus A transpose transpose. Okay, so what will happen now? So now what will happen is that half A transpose will come, and transpose of transpose is again the original matrix. Then what will happen? I will write the minus sign outside. It. So A minus A transpose. Okay, and this is equal to your what? This is equal to your minus Q, clearly. Okay, so your Q transpose has come out to be equal to minus Q. Okay, so that implies that Q is skew symmetric matrix. Therefore Q is skew symmetric matrix. Now we will prove the uniqueness of this. Okay, we have just proven that any square matrix can be represented as a sum of symmetric and skew symmetric matrix. We have proven that. that it can be represented. Now we will prove that there is only one and one representation, only one representation. So condition of uniqueness we will prove now. Okay. So uniqueness. Now how to prove uniqueness? Let A is equal to R plus S be another representation. Let A equal to R plus S be another representation where R is symmetric and S is skew symmetric matrix. So we will basically take another representation and we will prove that representation to be equal to the original one. Okay, we will prove that this R plus S is not another representation. It has come out to be, this another representation has come out to be equal to the P plus Q representation. Okay, so if we prove that, then uniqueness will be proved. Okay, that any other representation will be same as the first one. Okay, so A equal to R plus S be another representation where R is symmetric and S is skew symmetric matrix. Okay, now we have to prove what? Now we have to prove that in order to prove the uniqueness, we have to prove that R is equal to your P and your S is equal to Q. Okay, so in order to prove that, we will simply take the transpose of A. Okay, so now A transpose, I told you just now that A is equal to your R plus S according to your assumption. So you took this transpose. Then A transpose is clearly equal to your R transpose plus S transpose. Okay, by distributivity. Then you know this very well that A transpose is equal to, as R is symmetric, so R transpose will be R, and as S is skew symmetric, so S transpose will be minus S. Okay, now A is equal to your R plus S according to assumption. Okay, and what is your A transpose? A transpose is equal to your R minus S. Okay, so clearly when we add these two, when we add A and A transpose, so you will get basically 2R. Okay, that implies that R is equal to half of A plus A transpose, and that is you are basically equal to the P, because P was also like this only, right? P was also like this, so you proved this. Similarly, when you take A minus AT, okay, similarly, let me write over here, okay, similarly, when you take A minus AT, what will it look like? When you take A minus AT, you get 2S, okay, so your S will be clearly half of A minus AT, okay, and this clearly proves that it is equal to basically your Q, okay, so hence representation is unique. It is proved because we took another representation R and S, but those came out to be equal to P and Q itself. Okay, so hence the representation we can write. Hence the representation is unique. Is unique. Hence every square. So every square matrix can be uniquely written as a sum of, okay, uniqueness we proved, existence we proved, uniquely written as a sum of symmetric and skew symmetric matrices. Okay, now the property number second says that B transpose AB, okay, B transpose AB is symmetric or skew symmetric according according as A is symmetric or skew symmetric matrix. This clearly means that if A is your symmetric matrix, then B transpose AB, okay. So let me write over here with a different colored pen, okay. B transpose AB is equal to symmetric. When it is symmetric, when A is symmetric. And it will be skew symmetric. It will be skew symmetric when it will be skew symmetric when A is skew symmetric. Okay, so this is the thing which we have to prove. Okay, so let's write the proof of this. Proof. So the first step towards proving symmetric or skew symmetric is very simple, that you have to simply take the transpose. Now as these three matrices are multiplied and its transpose is being taken, so by the property which you must have learnt by now, okay, which you must have got in your heads by now, is this property, okay, that A B transpose is equal to B transpose S A transpose. Which property? This is by this property, A B C transpose is equal to your C transpose B transpose A transpose. Okay, this is your property. So by that property you got this. Then the second step, B transpose A transpose. Transpose of transpose is original matrix, so B will be original. Now you can clearly look at this. Okay, suppose A is symmetric. So suppose A is symmetric, then what will happen? It will become like this. If A is symmetric, okay, if A is symmetric, it will become like this. Two situations arise, okay, in case of symmetric, okay, and the other situation arises something of this kind, okay, if A transpose is equal to minus a. That is skew symmetric. Okay. Hence, so it is clearly proved that B transpose A B transpose A B transpose. So it is coming to the original matrix. Okay, it is coming out to be equal to the original matrix in case of what? In case of A being symmetric, and if A is skew symmetric, then it is coming out to be equal to minus B transpose AB. That is, it is also skew symmetric. Okay. So if A is symmetric, it is also symmetric. If A is skew symmetric, it is also skew symmetric. So clearly, this is proved basically. Hence, hence B transpose AB is symmetric or skew symmetric according as A is symmetric or skew symmetric matrix. Okay. Now we will talk about conjugate of a matrix. Okay. Conjugate of a matrix. So write down the definition of conjugate of a matrix. Okay. Just a second. Let me have some water. Yes. So let's move on towards conjugate of a matrix. Okay. So write down conjugate of a matrix. Conjugate of a matrix. Okay. The conjugate of a matrix A is obtained by changing the sign of iota, that is I, and it is denoted by a bar. Okay. So to find the conjugate of a matrix, whatever elements are there in the matrix, just change their iota sign. If suppose all the elements of the matrix are real, in case if all the elements of the matrix are real, then the conjugate will be same as the original matrix if all the elements are real. But if some imaginary elements are also there, means complex elements are also there, that means iota sign will be present. In that case, wherever you find iota, just replace it by minus I. Okay, but just replace iota by minus iota, and you will get the conjugate of the matrix A. Okay, it is denoted by A bar. So if I take an example, so suppose I have this as my matrix. Okay, so in this matrix, when I try to take its conjugate will be same as the original matrix. Okay, its conjugate will be same as the original matrix. Why? Because there is no imaginary term, no iota term present here. But as soon as I introduce an iota term, suppose 1 plus I is there. Okay, suppose I introduce an iota term. Okay, means imaginary term. So suppose I introduce 1 plus I, then what will happen? This I will be replaced by minus I. So when I will be replaced by minus I, the conjugate will look something like this. Okay, so this is the thing. So let's look at the example. Okay, so example is very clear. Okay, you must have learnt in lower classes during the time of JE, during the time of IIT JE, you must have learnt that the complex conjugate of a complex number x plus iy is given by x minus iy. Okay, where x and y belong to real set of numbers. Okay, real set of numbers. Now properties of conjugate of a matrix. Let's write properties of conjugate. Properties of conjugate of a matrix. Okay. Properties of conjugate of a matrix. So property number one, we will look at the properties without any proof. Okay, we will look at the properties of conjugate without any proof. So a plus b whole bar is equal to your a bar plus b bar. Okay, if we look at these proofs, then it will be very much lengthy. Okay, your syllabus will not be completed on time if we look at the proofs of all these things. So just ignore the proofs. Okay, where k is any scalar, where k is any scalar, whether real or complex, real or, if k is real, suppose k is real, if k is real, okay, so write if k is equal to real, k bar will be equal to k. Okay, but if k is not real, okay, if k is not real, then k bar will not be equal to your k. Okay, so this is the thing. Now the third property. Third property is ab bar is equal to, means ab conjugate is equal to a conjugate b conjugate. Okay, and when we take the conjugate two times, when we take the conjugate two times, then we reach at the original matrix. Okay, because one time changing the sign will give you minus iota, then other time changing the sign will give you back plus iota. Okay, so these are the properties. These are very much common sense properties, so I don't think there is any need to prove this, and the proof will not be asked in the examination, by the way. Okay, now let us move on towards the tranjugate of a matrix. Okay, tranjugate, tranjugate of a matrix. The transpose of conjugate of a matrix. Okay, the transpose of conjugate of a matrix. The transpose of conjugate of a matrix is called tranjugate of a matrix. Means first we will take the conjugate and then we will take its transpose. We will take the transpose of the conjugate. So transpose of conjugate of a matrix is called tranjugate of a matrix. Okay, so it is denoted, it is denoted denoted by a theta. Okay, a theta or a star many representations of it are there, okay, or A transpose, then we take the conjugate, or A conjugate transpose. So all these things mean the same. This thing, various representations are there in the textbooks. Okay, various representations are there in the textbooks, but all these four representations mean the same. Okay, all four is equal to same, means all the fours mean the same thing. Okay, now what does it mean by conjugate? It is very clear that we will take the conjugate first and then we will take its transpose. Okay, so let me write over here, take conjugate of a matrix by by changing the signs of iotas. Okay, take conjugate of a matrix by changing the signs of iotas. Okay, then after after conjugate is taken, take its transpose. Take its transpose. That implies what? That implies conjugate. Okay, that implies conjugate. So properties of conjugate of a matrix, write down. But over here we are going to use this notation, this particular notation. Okay, in our classes we are going to use this notation. Okay, a theta. Okay, a theta we are going to use in our classes, because in 90% of the textbooks a theta is given. Okay, the other representations are not much used. A theta is the most commonly used representation, so that's why we will use that representation. So properties of conjugate of a matrix. Properties of conjugate of a matrix. Properties of conjugate of a matrix. So let A and B be two square matrices. Be two square matrices of same order. A and B are two square matrices of same order. So if this is 2 cross 2, then this will also be 2 cross 2. If this is 3 cross 3, then this will also be 3 cross 3. Okay, if this is 4 cross 4, then this will also be 4 cross 4, like that. Okay, so that's the meaning of square matrices of same order. Okay, so let me erase these things. Okay, so if let A and B be two square matrices, let A and B be two square matrices of same order, then okay, this is same, then what will happen? Then the following things will happen, which are given on the next page, that is the properties. Okay, then this is very important fact, that they must be of the same order. Okay, otherwise these properties will not hold good. Okay, if they are not of the same order, then these properties will not hold good. So A plus B conjugate, A plus B conjugate is equal to your A conjugate plus B conjugate. Okay, then second property is A conjugate, and when its conjugate is once again taken, then you get the original matrix. Okay. Then the third property, Ka conjugate, gives you K conjugate A conjugate. Okay. So this is what? Ka conjugate. Okay. So this is basically Ka, Ka's conjugate, Ka's conjugate is equal to K conjugate multiplied by A conjugate. Okay, this is the meaning of this. Means when you take the conjugate of Ka, it is equal to K conjugate multiplied by A conjugate. Okay, this is the third property. And over here, K is equal to what? Okay, let me write over here. K is equal to what? K is any scalar, real or complex. Okay, K is any scalar, real or complex. K is any scalar, real or complex. Then the fourth property, we have something of this kind. AB conjugate. Okay, AB conjugate is equal to B conjugate A conjugate. Okay, AB conjugate is equal to B conjugate A conjugate. Now we will move on towards our next topic, which is the Hermitian matrix. Okay, what is Hermitian matrix? Let us move on towards what is Hermitian matrix. Okay, a square matrix, a square matrix A is equal to Aij. Okay, as it is a square matrix, so what will it be called? N cross n order. Okay, a square matrix A equal to Aij, n cross n is called Hermitian. Is called Hermitian matrix if and only if I double f if. Okay, if I double f if means if and only if. So a square matrix A equal to Aij n cross n is called Hermitian matrix if and only if your A conjugate, if it comes out to be equal to A, then your matrix is Hermitian matrix. So that is, which is the same as A conjugate comes out to be equal to A is same as Aij is equal to Ji. Okay, let me write properly. Aij equal to Aji conjugate for all I comma j. Okay, this is by common sense, because what is conjugate? You will first take the conjugate and then you will take the transpose, right? You will first take the conjugate and then you will take the transpose. So when you take the transpose, j and I will be interchanged. When you take the transpose, j and I will be interchanged. And when you take the conjugate, bar will come. Okay, so that's why this property has hold good over here. Okay, this property has hold good over here, that's why. Okay, so in other words, you can write like this also, or you can write this also. Okay, for all I comma j, that is the you will check the diagonally opposite elements. Means diagonally opposite means, if suppose this is the principal diagonal, then you will check the elements here and you will check the elements here. Okay, this element and this element should satisfy this condition, this element and this element should satisfy this condition, and this element and this element should satisfy this condition. Okay, so that's how your Hermitian matrix will look like. Okay, So so let's move on towards the properties of Hermitian matrix. Okay, properties of Hermitian matrix. Properties of Hermitian matrix. Okay, in case of Hermitian matrix, the first property is, in case of Hermitian matrix, in case of in case of Hermitian matrix, all the diagonal elements are real. Okay, all the diagonal all the diagonal elements are real. Okay, so diagonal elements must be real. Okay, how? Over here you can write aii. Okay, aii equal to real, aii belongs to real, or you can write like this, for all. Okay, for all, that means, let me write over here, for all I. Okay, so aii, this is also a condition which it must satisfy. Okay, so in case of Hermitian matrix, all the diagonal elements are real. So let's look at the proof of this. Let's look at the proof of this. Proof. Let A be Hermitian matrix. Let A be Hermitian matrix. So by the definition of Hermitian matrix, A theta should be equal to A. Okay, by definition. Okay, by definition of Hermitian matrix. So that is, your Aij should be equal to your Aji conjugate, right? Now for all I equal to, not for all I equal to j. Okay, so for all I comma j, so that will also imply that I comma j. So that implies that this will also hold good. This will also hold good for I equal to j, because for diagonal elements I equal to j, right? So this will also hold good for I equal to j, that is diagonal elements. Yes. So what will happen? What will happen then? Eventually aii will be equal to your aii conjugate for all I, right? Because I equal to j, so you will write it like this. So that implies that aii is equal to real. Okay, aii is equal to real for all I. Now how did this come? How did this result come? You know this very well. You know this very well from the fact, from the fact that, from which fact? From the fact that the conjugate of a real number is equal to the number itself. Okay. So from the fact that conjugate of a real number is equal to the number itself, we can clearly say that ai is your real for all I. Okay. So all the diagonal elements of a Hermitian matrix, so we can write that all the diagonal elements, all the diagonal elements of a Hermitian matrix are all the diagonal elements of a Hermitian matrix are real. From here we can prove this. Now we will look at the proof of this. Proof of what? We will look at the proof of this, that if such a condition arises that conjugate of a number is equal to the number itself, if conjugate of a number is equal to the number itself, then uh, then when conjugate of a number is equal to the number itself, then such a number is a real number. Okay, then such a number is a real number. We will look at that. So note note let note write in the note, let z is equal to x plus iy. Then what will happen? Then z bar is equal to your x minus iy. Okay, by the definition of conjugate. Case 1, if z is equal to z bar, suppose, then what will happen? X plus iy will be equal to your x minus iy, right? So that comes out that 2iy is equal to 0, because x and x will cancel out. X and x will cancel out from here. So 2iy is equal to 0. That implies your y is equal to 0, right? So what is your z? Your z is equal to basically x, because y has come out to be equal to 0 and x is real. So that implies z is real. Okay. Now case number 2. If z is equal to your z bar, suppose, minus z bar, suppose. Okay. Then what will happen? X plus iy is equal to minus of x minus iy. Okay. So what will happen? X plus iy is equal to your minus x plus iy. So iy will cancel from here. Okay. So your 2x is equal to what? Your 2x is equal to, that implies your 2x is equal to your 0. That implies x is equal to your 0. So z is equal to x plus iy now. So we will put x equal to 0. So that will be equal to iy. So z is purely imaginary in this case. Okay, so you have to remember this property. Which property? Property. Which property? This property, that when z is equal to z bar, means conjugate of a number is equal to the number itself. That implies the number is real. And when conjugate of a number is equal to minus of that number, means sign inverted. Okay, then what happens? Z is purely imaginary. Okay, imaginary. So these are the some of the facts which you must remember. Now let's move on towards our property number 2. Okay, so let's move on towards our property number 2, but before that let me have some water. Okay, just a second, I am coming back. Yes, so have a look at the property number 2. Property number 2 says that in the case of Hermitian matrix, all the elements above and below, all the elements above and below the principal diagonal are equal but the sign of imaginary part but the signs of imaginary parts are opposite. Okay, let's take an example. Suppose I have a matrix of this kind. A is equal to, okay, L M N. Okay, so what does this say? In case of a Hermitian matrix, it is a property of Hermitian matrix that all the elements above and below the principal diagonal. So this is your basically what? This is your principal diagonal. Okay, this is your principal diagonal. So all the elements above and below the principal diagonal are equal. Okay, so the elements above and below the principal diagonal will be equal. But the thing is, the sign imaginary part sign will be opposite. Okay, equal means equal in magnitude. Okay, how do you find the magnitude of an imaginary quantity? You take the square root of real parts, right? Square root of sum of square of real parts. So magnitude are equal of this complex number. Okay, but sign of iota is opposite. Okay, x3 minus I by 3. So this is your principal diagonal. This is your principal diagonal, and this is 3 cross 3 matrix. So the over here it is x1, over here also it is x1, over here it is y1, over here also it is y1. So magnitude is equal, but sign is opposite. Over here it is plus, over here it is minus, over here it is plus, over here it is minus, over here it is plus, the iota sign is plus, over here the minus sign is there for iota. Okay, so all the elements above and below the principal diagonal are equal. Actually we should not write equal, we should write equal in magnitude, are equal in magnitude. Okay, in magnitude. Why equal in magnitude? Because they are not equal but their magnitude is equal. Suppose I take x1 plus I y1 and I take x1 plus I y2 minus, okay, minus x1 minus I y1. Okay, suppose I take x1 plus I y1 and x1 minus I y1. Then the magnitudes will be, what will be the magnitude? X1 square plus y1 square. This will be the magnitude of both of them. Both of them will have the same magnitude. So are equal in magnitude, but the signs of imaginary parts are opposite. So x1 minus I y1, for that also your magnitude will be square root of x1 square plus y1 square. Okay, so magnitude are equal, but the signs of iota are opposite. Okay, this is y1 by the way. Okay, so this is property number 2, which all of you must remember. Now the third property. If A and B be two Hermitian matrices, if A and B be two Hermitian Hermitian matrices of same order, then A and B are two Hermitian matrices of same order, then K1A plus K2B is also Hermitian matrix, is also Hermitian matrix for some real scalars. K1 and K2 must be real, this is compulsory. K1 and K2 cannot be imaginary. Okay, for some real scalars K1 and K2. So if A and B are two Hermitian matrices of same order, okay, then K1A plus K2B is also Hermitian matrix for some real scalars K1 and K2. Okay, now let's write the proof of this. Proof. In order to prove the Hermitian that K1A plus K2B is Hermitian, okay, in order to prove that K1A plus K2B is Hermitian, we have to prove that its conjugate is equal to K1A plus K2B. If the conjugate comes out to be the same, okay, then it will be by definition of Hermitian matrix. By definition of Hermitian matrix. Okay. So what will happen? So something of this kind will happen. K1A plus K2B conjugate. It will come out to be your K1A conjugate, okay, plus K2B conjugate. Then by the property which I had told you, K1 conjugate A conjugate plus K2 conjugate B conjugate will come, right? Then conjugate of K1 and K2 are real scalars. K1 and K2 are real scalars. So conjugate of K1 will be K1 itself, okay? And conjugate of K2 will also be K2 itself. And what about conjugate of A? Conjugate of A will be A. Why? Because A and B are Hermitian, okay? and tranjugate of B will be B, because A and B are Hermitian. Okay, so tranjugate of A is A, tranjugate of B is B, as A and B are Hermitian. Okay, so write over here K1 and K2 are real and A, B are what? And K1 and K2 are real, and also A and B are your what? A and B are Hermitian. Okay, A and B are Hermitian. So this is the thing. So from here we can clearly see that as your K1A plus K2B tranjugate is equal to your K1A plus K2B. So what does this imply? So this clearly implies that K1A plus K2B is also Hermitian matrix. Is also Hermitian matrix. This is by definition. Okay, by definition of Hermitian matrix. This is by definition of Hermitian matrix. Now let us move on towards our fourth property. Okay, if A be Hermitian matrix, if A be Hermitian, if A be Hermitian matrix, then Ka is also Hermitian matrix for some real k, for some real k. Okay, so if A is Hermitian matrix, then some scalar k, some real scalar k multiplied by A will also be Hermitian. We have to show this. So proof is as follows, that Ka tranjugate, if the tranjugate comes out to be the matrix itself, then it will be clearly your Hermitian. Okay, so this is the thing. Okay, so conjugate of k will be k only, because k is real. So conjugate of a real number is the number itself, and tranjugate of a will be a. Why? Because a is Hermitian. So you can write over here, because a tranjugate is equal to a, because a is Hermitian and k is real. Okay, so that's why your Ka, by definition of Hermitian matrix, Ka is Hermitian matrix. Now fifth property. Okay, fifth property, every real symmetric matrix is Hermitian. Okay, every real symmetric matrix is Hermitian. Every real symmetric matrix is Hermitian. So proof of this, Real symmetric matrix means, real symmetric matrix, what does it mean by real symmetric matrix? Real symmetric matrix means, you know the definition of symmetric matrix, that when transpose is taken, okay, when transpose is taken, it comes out to be the same. A is equal to A transpose. That is called as symmetric matrix, right? So every symmetric matrix is Hermitian. We have to prove this. Now, what is meant by real symmetric matrix? All the elements will be real. That's why it is called as real symmetric. Symmetric means A transpose will be equal to A. Okay. So such a matrix is Hermitian also. We have to prove this. Let A be real symmetric matrix. Let A be real symmetric matrix. Then what will happen? By the definition of symmetric matrix, we have something of this kind. Okay. Now we will take the conjugate on both sides. What we will take? We will take conjugates on both the sides. So I took the conjugate over here. So on the right hand side also I will take the conjugate. Okay. Now by the definition of conjugate, this is basically your what? This is your conjugate. Okay. This is your conjugate by the definition of conjugate. So that has come out to be A conjugate is equal to, now conjugate of A, what will be conjugate of A? All the elements are real, okay, all the elements are real, so conjugate of A will be equal to A, because all the elements are real, right? So even if you change the iota sign, okay, if you try to find out the conjugate of A, you will change the iota sign, but there is no iota sign at all here, because all the elements are real. So A conjugate will be equal to A, because right over here A is real symmetric matrix, okay, A is real symmetric matrix. Now by the definition of Hermitian matrix, from here it is proved that A is your what? Hermitian matrix. Okay, because this is the definition of Hermitian matrix, that conjugate should come out to be equal to the same matrix. So as conjugate has come out to be equal to A itself, so A is your Hermitian matrix. A is Hermitian matrix. Okay. Then we have something called as I won't go into the proofs of all this, but you can prove all of this yourself. Okay, you have to prove all of this yourself. Sixth and seventh property you have to prove yourself, your homework. Okay, let A and B be two Hermitian matrices, be two Hermitian matrices. Let A and B be two Hermitian matrices of same order. Let A and B be two Hermitian matrices of same order. Then what will happen? Then AB plus BA is also Hermitian matrix. AB plus BA is also Hermitian matrix. Okay, so A and B are two Hermitian matrices of the same order. Then AB plus BA is also Hermitian matrix. You have to prove it yourself. It is very easy to prove this. Okay, it is very easy to prove this. Now seventh property. If A and B be two Hermitian matrices, of same order. This of same order is very important over here. Okay, then AB is also Hermitian matrix. Then AB is also Hermitian matrix if A and B commute. Okay, if AB is equal to BA, that is A and B commute. Okay, this is called commutative property. AB is equal to BA is called commutative property. So if that is A and B commute, if they commute, then if A and B are Hermitian matrices of same order, AB will also be Hermitian if AB and BA commute with each other. Okay, now the eighth property, the proof of which I am going to give you. Okay, the eighth property now, if AB any square matrix, if A B any square matrix, then if AB any square matrix, then A conjugate A conjugate A and A plus A conjugate are also Hermitian matrix. Are also Hermitian matrices. If A B any square matrix, then A conjugate A, and A plus A conjugate are also Hermitian matrices. You can prove it yourself. Okay, it is very easy to prove this. So let's take one over here. Okay, let's take one example over here. Okay, so I am taking this example. So it will be clearly your like this. So what will happen? A conjugate will be there. A conjugate will be again A by the property which we have already learnt, and then I will change the order and write it. Okay, so clearly as this is equal to this, so that implies therefore A plus A conjugate is Hermitian matrix. A plus A conjugate is Hermitian matrix. Okay, ninth property, all positive integral powers. Okay, all positive integral powers of Hermitian matrices are also Hermitian. Okay, what does this mean? Suppose A is your Hermitian matrix. Okay, then what will happen? All positive integral powers. Okay, so suppose I take A to the power n, I take. Okay, so n is equal to your positive integer. Positive integer means 1 2 3 4 and so on and so forth. Okay, so all positive integral powers of Hermitian matrices, that means A to the power n is also also Hermitian. Okay, also Hermitian matrix. So prove it yourself. Okay, prove it based on lecture number 3 and 4, whatever we have proved there. Using that you can prove it. Okay, prove it yourself. And property number 10, this also you have to prove yourself. If, because they are on the same lines, okay, they are exactly the same, no difference is there. If A and B are Hermitian matrices, if A and B are Hermitian matrices, then BAB is also, okay, then BAB, then let me write over here properly. Okay, then then BAB is also Hermitian matrix. Okay, BAB is also Hermitian. So if A and B are Hermitian matrices, then BAB is also Hermitian matrix. You have to prove it yourself. Okay. Now let's move on towards our next topic, which is skew Hermitian matrix. Okay. But before that, I will have some water before moving on to skew Hermitian matrix.